We are live.
All right, everyone. Welcome to another Wolfram Institute live science stream. Today, we're continuing our conversation with Carlos about his work on what in the past we've been calling subaxiomatic foundations of mathematics. But with time, we've come to, I think, adjust our description, not because we've abandoned uh, the ambition of going subaxiomatic, but rather as we attempted to probe this notion of subaxiomatic foundations, we discovered kind of a more interesting formalism and structure by which we can describe what it is that we're doing. It involves these things called complexity categories that we're developing, as well as a much more rigorous study of hypergraphs. And so I received a nice email from Carlos on Friday with a kind of a document outlining with formalism many of the ideas at play, which is great. I love documents. I love lists. I love things being organized. I imagine maybe Carlos has even developed it further since then. So, Carlos, what I'd like to do today, I think we should all do this together, is let's just look over this document, discuss, comment. I'm sure you have commentary, like things that haven't been added, things that you want to add, et cetera, et cetera. So we have an hour. Let's dive right in.
All right.
Ready?
So, yeah, as a very brief preface to actually talking on the document, which I'm going to share in a second. Can you all see that?
Not yet. Yes. I can see it.
So I'm going to put your faces so the stream is actually nice. Okay, so yeah. So as a preface, I want to say that, of course, this hypergraph part of the project of what I'm currently thinking to do in the institute is just kind of an instrumental part of a much larger, broader sort of goal that we have, which of course is this idea of thinking of formal systems and emulation between formal systems and having this concrete computational and operational access to the Rulliad, right? So this idea that we might get there. So hypergraphs have appeared both from the physics project and the fact that they are sort of a rising concept in several areas as this data structure that seems to be very well fitted for our needs. And so I suggested to James, and then I put into this document this kind of preliminary work that in itself can be a very good development of having sort of hypergraph theory implemented computationally and quickly going into the direction of complexity of hypergraphs. And so we have these ideas of complexity relations and complexity measures and so on. So the document itself, in the contents, you can see basically what I intend to cover eventually, and I intend to sort of summarize everything we do here and put it in a copy-friendly format. So if we ever want to write up maybe some blog post or maybe some paper or whatever it is, it's easy to just extract from the LaTeX file, which is plain text mostly. So motivation, some preliminaries. Now, the kind of so perhaps let me just briefly comment on the structure. So there is a bulk of content in this document that is meant to be just about hypergraphs, right? It's going to be just basic hypergraph theory, which any mathematician or anyone, scientist, physicist, whoever who is intending to learn about hypergraphs could follow, right? So you can just get into it. You can learn the very basic notions, and I mean it assumes. I mean, it's going to be written in a fairly condensed, compact way, so it's not going to be completely pedagogical, but it will not assume, knowing exactly what all these things are and, having had several, courses on set theory and discrete maths or anything like that, right? Now, when it comes to, so then this bulk will be basically the preliminaries, basic definitions, hypermatrices, So for hypergraphs, it will be preliminaries and basic definitions. So that's where the bulk of hypergraph technology will reside. And then after that, I've listed some of the areas that we've identified as important, and we've somehow commented at some point. So if I have hypermatrices as sort of the computational or algebraic dual of hypergraphs, then motifs as all these questions of pattern detection, pattern matching, embeddings, all these kinds of questions that we discussed. Taxonomy for all the questions relating, very general questions relating to classifications, classes of hypergraphs, types of hypergraphs, subclasses of hypergraphs, all those kinds of things. And then metrics, which is anything to do with sizes, anything to do with counting on hypergraphs. Like that's kind of the hypergraph metrics is what I normally understand combinatorics people think of hypergraphs as, right? Like most combinatorics people think of hypergraphs as this combinatorial objects that allow you to very efficiently count stuff. And if you read any hypergraph papers in this side of the fence, they mostly count stuff. So all that goes to metrics, things that you can count on hypergraphs because they are discrete objects and you can count stuff. Then the categories section, I intend to both the identification of categories of hypergraphs, which is kind of an implied definition from the basic definitions in section 3, but then also anything to do with categorical treatments of hypergraphs. This goes from anywhere from how we're going to implement this complexity metrics as James wanted into the morphisms of some kind, all the way to people who are doing compositional structures with like a monad that it takes hypergraphs and all these kinds of stuff, right? And the rewriting stuff and everything. And then maybe the category should be below rewrites in some sense. Then the rewrite section is dedicated exclusively to just anything rewrite. So there will be some general rewrite theory in there that is sort of not specific to hypergraphs, just sort of an introduction. And then obviously everything to do with hypergraph rewrites. Because as I said, I think the taxonomy section and the rewrite section are going to be quite related because a lot of the classification of hypergraphs and the typing that we want to do of sort of going into these kinds of other kinds is going to depend on the kind of rewrite rules I want to implement, right? Because if it's undirected or is it whatever. And then
so let's just make sure I understand. So at some point we'll have a report that addresses the key question about emulations and the questions that originally motivated the study of subaxiomatic foundations. Now, as we've learned rather quickly, that final report, that final study will make use of formalism, even concepts, categories, measures, etc., that we ourselves have to invent.
Yep.
And so I can imagine that this is kind of like a formal technical document that taking hypergraph theory as its subject matter is providing an overview and a rigorous introduction into these inventions that we're making in these techniques that we're using, so that we can have this document. We can also have a separate document on the study of emulations that's more readable, and you can just tell the reader, and refer back to this technical document to learn about how we develop this complexity measure in greater detail, or category of hypergraphs in greater detail, or if you want to learn about hypergraphs, you can refer to this technical document in greater detail. Is that the idea? That as we're developing this scaffolding, technical scaffolding, is being summarized and developed in this document? Is that the idea?
Yes. So that's basically the idea. I will refine what you just said by adding that this particular document is something that this is normally how I record when I understand something. If I know something in mathematics, I just write and I record it, right? So I would, even if nobody's willing to get into the LaTeX and just write the stuff, if something gets done for the hypergraph that is relevant for the hypergraphs, then I will put it in here. Because, for example, the complexity and computation sections, I would imagine that in the beginning, other people will have something more to say than I will, because I will be mostly sort of developing the core sort of hypergraph, motif, taxonomy metrics, and so on, to have the document sort of filled with these concepts, right? So if something else gets, for example, in computation, some functionality, Nick makes some function, or Richard has some idea for an algorithm or something like that. If this is discussed and this is established and we all agree in some meeting, okay, yeah, this looks good, this works well, then I'm gonna go and go there and type it up and put it there, right? So this, to me, this document, this particular document that I'm showing, is kind of the Bible, the sort of theoretical Bible of this particular sub-project of the subaxiomatic or xenoaxiomatic or whatever foundations. So
Or the Kabbalah or whatever you guys want in the audience.
So it's kind of the record, right? Is the recorded in stone knowledge that I have about the subject. Now, obviously, the idea is that it is written. The way I write my notes is in a way that they are very reusable, so that you can just easily bring them to something like, what is the hypergraph project, and then you have a 3-page document and you're extracting here and there, or you have a website post somehow that has a lot of this stuff, right? So it's not meant to be, I mean, you can read the whole thing and it should be more or less readable and more or less structured, but it's mostly this record of established theory. And so we can refer back to, and it has a lot of references. That's the thing, that it's also filled with references. So it's kind of the nexus point for the theoretical needs, right?
Good. I like this impulse. This is a good idea.
Okay.
Why don't we inspect the contents?
Yeah. So the contents are basically, so the most relevant, perhaps, decision point that I made regarding regarding the contents that are in the document is the definition of hypergraph, right? So a lot of people can take many different definitions of hypergraph. In my opinion, the most natural way to go at this, especially because we are computationally minded and we are eventually going to implement some functionality, is to use multisets. And so using multisets basically means that we are by default considering collections of objects, which are essentially like unordered lists in Mathematica, and so they have repeats, right? So all this introduction is basically to mathematically ground what a multiset is, which is a completely trivial, easy concept, just a set with a multiplicity function, nothing mysterious there. And then all these definitions effectively capture the idea that once you have a collection of objects, you can make different data structures out of them, right? So I make the summary here. I make the reference to combinatorial species. This is the other technical point that I would probably expand on. There will probably be a subsection about combinatorial species at some point, because I think the theory of combinatorial species just has everything that we need. So if you or the audience people have not heard of combinatorial species before, this is just a general framework to include this notion of order structure of elements, right? So you have two ends of the spectrum. Whenever you have a collection of elements, you have what we're calling the bags, which are unordered collections where repeats can happen, and then there are tuples, which are fully ordered collections of elements where repeats can happen. Right? So in between these two, there's a rich sort of universe of possibilities, right? And one of them being obviously trees, cycles. There are many intermediate possibilities, like for example tuples of bags, so you can have something undirected into something undirected, and that's what people call directed and things like that, right? So all that theory is contained in the combinatorial species literature. I think it's basically ready to use. We don't have to really develop much. For us, the only thing that matters is that given a collection of objects, if you're thinking of them in this context of multiset theory, so they can have repeats, which is very natural, then you can construct an arbitrary data structure out of it that has two properties, and this is the most important part, is that, well, bags has this cardinality grading, right? So given a collection of elements, a bag of elements always carries a number, which is the cardinality of the bag, right? It's the number of elements of that bag. So think of how in tuples you always know how many products you're taking, right? If you take a 2-tuple or a 3-tuple or a 4-tuple, etc. A bag is exactly the same thing, but it has no internal structure, it has no order inside. So the idea of a general combinatorial species, what I call a mix, because it's a much shorter word, a mix of elements is a general structure that has two things. It has a type, so type meaning, is it tuple, is it a bag, is it a cycle or whatever, and it has a projection on a bag, right? So it has a base bag, which is basically its contents, right? And so that has a number because bag has a cardinality. So that's basically what a mix is for us. Now, once we have the definition of mix nailed down, then the definition of hypergraph is fairly straightforward. I mean, and this is where we differ from some literature, because we're working over mixes instead of either tuples or sets or something like that, which is of course all a particular case of our case. So the definition of hypergraph then has a basic collection of elements and then a multi-set of edges, right? So,
hey, will you do me a favor, Carlos? Will you zoom in a little on your screen?
Oh yeah.
The margins are pretty fat.
Yeah.
I'm squinting a little. Ah, that's much better.
Yeah,
that's way better. Thank you.
I'm just gonna fix your faces so that stream can
fix my face. Ouch.
Yeah. Sorry. Yeah. I have a very big screen. I have no issue, but yeah, I can imagine. So, right. So, hypergraph, very simply, collection of vertices. Think of them as labels, essentially, sort of distinct, unique labels, and then a collection of edges, right? So, edges are going to be made of mixes of vertices. So, and the edge set is a multiset, so it means it can have repeats, because we are going to, in principle, define unlabeled hypergraphs to begin with. And then this basic definition section establishes a lot of conventions these are as closely following the standard as possible. So if you remove or if you replace mix by set and you replace multiset by set in all instances, you should recover the definition of the conventional definition of hypergraph. If you replace mix by list or ordered list or tuple, then you would recover the definition of hypergraph in the physics project, for example, right? So it's as close as possible as to the standard hypergraph conventions. The only thing that is a little bit new is this idea of homogeneous and heterogeneous, because that's normally people don't consider different types of edges. They are all the same type, just different orders. Now we have different orders and different types, but whatever. Now K uniform, all these things are fairly standard. Then definition of a hypergraph map basically requires you to keep track of types, right? You need to preserve edge types and edge cardinality. So it's an absolutely natural thing, and so there's a bunch of stuff missing here, which is fairly automatic. Like once you define these things, how to do additive union of hypergraphs, how to do Cartesian product hypergraphs. I mean, there is some subtlety in Cartesian product hypergraphs. This is not a closed question. In fact, there's no consensus in the community. I mean, different definitions of hypergraph have used different definitions of Cartesian product. So we might need to discuss this a little bit and to think about it carefully. And then, of course, there are order reductions, which we have mentioned in the past, which is this idea that if you have a higher order hyperlink, you can just take the sub mixes of the elements or the subsets of the elements, and you can take them as new hyperedges. So again, type dependent, but otherwise quite clear. Now the hypermatrices, this is something that I had worked on a little bit before. So we have this theory of arrays that I actually developed with Tali. For those of you who know him, and we basically have this generalized tensor network formalism. It is very standard. There's nothing different from standard tensor network formalism, other than the fact that we explicitly allow for multi-index contraction. So we can, in particular, sum over the same index, the same vertex of a hypergraph many times, and then so this is also.
Whoa, that was fast.
Yeah, these are all generalities about array algebra. I mean, I don't think it makes much sense to go into the depth of the detail.
Fine. Okay. You have a goal. Keep going.
Yeah. So what I would say about this is that all we do here is we define. Okay, let me very quickly say what an array is. So for those of you in the audience who are unaware, so an array is basically a assignment of values from a collection of indices, right? So if you have and an index is just, for me, is just a finite set, basically. And so if you have a value for me is something that can be operated like a number. So it's an element of a semi-ring, right? So if you choose a semi-ring and you have some finite sets, then maps from collections of these sets into the values are arrays, right? right? So if you can imagine, you put things tidily, then you arrange them in some kind of spatial tables or hyper tables, and then they have numerical values in their entries, right? So this is really trying to generalize the theory of vectors and matrices that everyone is familiar with. And as I said, we take a very parsimonious approach in that the general operation that we define is always tied to the fact that indices might be incident or non-incident. And that means that you begin with a collection of index sets, or what I call indices in singular, right? So you have a collection of indices, and each of them is just a set. And you have arrays of scalars that bind collections of these. So this is what we call index constellations, right? Which are just arrays, right? And the idea is, if two arrays are set in two different constellations, they might or might not share common indices. So if they share common indices, there's where you can define operations. Because otherwise, you need some condition beyond just the fact that these objects have algebraic nature to define operations. Because you say, well, they are numbers, you can always multiply them. Well, yes, but we need some structure beneath it. The structure is this idea of incidence, right? The fact that indices might be in common or not. And so that's why we have additive incidence, multiplicative incidence, and in general, the incidence will be assumed to be multiplicative, because we are normally taking the view that arrays of the same order are vectors in some vector space. So we use the usual theory. And then we also have contractions which basically mix.
Carlos,
Yeah.
do you have a definition of an incidence matrix, like similar for the graph? You have a similar notion for the incidence matrix for a hypergraph, right? You just a matrix with a number of hyperedges and a number of rows, number of vertices, hypervertices, or the number of columns.
Yeah.
So
this is
of a hypermatrix.
Yeah, so this is just a coincidence in naming, I would say, because this is just purely hypermatrix or array algebra stuff. It's not referring to hypergraphs directly at this point, right? So this is just a name to say that you have an additive incidence between two arrays. It just means that they have at least one index in common, and you're summing along the index.
So I understand. I'm just asking whether you define something like an incidence matrix for graphs, but hypergraph version.
And not by that name. I don't define, not by the name of an incidence matrix.
But you have something like a matrix.
He's saying irrespective of the name, do you have something like that?
Yeah.
Well, we have the adjacency matrix. I don't think we have the incidence matrix.
Okay. I just over this weekend I come up with some function that just makes an incidence, something like an incidence matrix.
Yeah, for sure.
Goes back and forth.
For sure. Yeah. I mean.
Okay.
It's just a representation of a hypergraph in general.
Yeah. So anyway, I was building towards the fact that we do this algebra. This is all pure array algebra, nothing to do with hypergraphs initially, and there's some explanation about different products and whatnot, self-incidences, identities, and Kronecker-like things, diagonals and things like that. It's some basic exploration of just arrays for their own sake, and then the connection is made with hypergraphs by noticing that if you take a hypergraph and a type. So you take a hypergraph and you fix an order and a type, then you can encode in the simple case, but in the more complicated case, we can just make a more complicated semi-ring. You can capture the hypergraph data precisely into an array, right? By fixed type and fixed order. So the general adjacency array, or what we call the hypermatrix, is given by this collection sum, right? Like this direct sum of, and we write it as a sum because we are assuming this vector space structure in sort of entry-wise, right? So this is, and then obviously here is where you would have everything that is on the hypergraph section should have a dual here. There will be a subsection about array algebra and then a subsection on hypermatrices of hypergraphs. And then you should have every single result that is a hypergraph result should be expressed here as a hypermatrix result, right? And obviously the great advantage of hypermatrices is that they are going to be, I think, much easier to work with computationally when actually doing any serious work with it. Okay, so that's the hypermatrix part.
Okay, so I guess, I mean, one kind of core question is, you're dissecting hypergraphs and also with this use of types, generalizing even beyond the definition that we've used in the past.
Mm-hmm.
The question is, the dissection, is its purpose solely to formalize, say, mathematically exactly the objects that we're working with, or can we, because we just scrolled over quite like 12 pages or maybe 11 pages of material. You know, some of these, can we scroll up a little bit?
Yeah. Where?
Well, even, I mean, these, let's just say the terms that you're emboldening here, you know, how often for some of these will they actually arise in the computations that we're doing? What I mean, for instance, is like hypergraphs. We can show computational examples of these. We could show computational examples of, you know, treatment with respect to like the guts of these hypergraphs or the particular properties. We could show examples. You know, one thing that I've said during previous meetings is we have an opportunity to have a kind of a unique style where, on the one hand, formally, mathematically, we're rigorously and adequately defining the objects that we're using, and we're also able to computationally provide examples or make the relations that are formalized in the notation more intuitive for people who like to think about things that way, which does include me. I like both. I like seeing things kind of shown statically, mathematically, and I also like seeing them kind of come to life through computational examples. But the question is, how much of this is setting the stage for computation? How much, you know, in what respects do these particular aspects of the hypergraphs, will they demand additional functionality on our part? Like, even, you know, you were suggesting, for instance, that this treatment is somewhat more general than the hypergraph functionality that we have, or sorry, more general than the definition that we have. So does that mean that the functionality that we have, in order to kind of match or correspond with this treatment, would you recommend that we generalize it or that we broaden it?
So
on the actual computation side.
So on the computation side, okay. So I was giving a very general comment on the mathematical side, but on the computational side, I was going to mention, and I think I included in some of the points that I wanted to discuss, like not the document, but like the sort of future of how to press forward and so on. Which was that we probably have to decide a class of hypergraphs to look at, because I mean, these combinatorial species, they are crazy general, and in some sense they are kind of fractal, because you can essentially have any kind of hypergraph as a combinatorial species, and that's kind of a sort of self-referential thing where each hyperedge can be itself a hypergraph, right? So because that's just the nature of it.
I see.
So, but that's, so this level of generality, I don't think it's really a problem. Like, I'm not trying to be a sort of an encyclopedist and try to catalog and like do everything. What I'm trying to do is
the cataloging is good. I just want to understand the interface between the catalog and the computational work, because when that interface arises, we can even include it in the document so that people can better understand how it relates to the computation side.
My idea is, because setting up these definitions is very cheap in some sense, some theoretical sense. I mean, these are the definitions that are going to apply to whatever we do.
Yeah.
So, but I'm not saying that we should develop functionality that is one-to-one to these mathematical definitions. What I'm proposing is that we develop this stuff and then we say, okay, now let's fix, for example, simple sequential hypergraphs, which is literally what the Wolfram physics project has been doing, right? So in that case, then we know we just have the technology ready, and so it restricts to that particular class of hypergraphs, and then that should be made computational, right? So it's not that we want functionality that basically translates all this theory into functions, but we want to say, well, what kind of hypergraphs do we want to look at? Because eventually we want to look at something that can be labeled hypergraphs so that we emulate the systems that we like, right? We encode the systems that we like, that we want. So I think that something like simple undirected hypergraphs is more than enough, but maybe undirected makes it a bit more expensive to use the existing functionality. On the other hand, Nick has mentioned how we should probably have some more primitive encoding of hypergraphs in any way, right? So I think that the natural starting point are simple undirected hypergraphs, because these are the direct generalization of sets, right? These are kind of relational sets where you have a set with some connectivity structure inside, right? So I think if there's not obvious application or recombination of functionality for that sort of framework, I think we should do that. I think we should develop it. I think we should have a language implementation for simple undirected hypergraphs, because then simple undirected hypergraphs with labels, I think, covers everything we need. Like it recovers everything we require for the Boolean algebra, for the SK combinator, for all those particular cases, right? So all these
Nick,
definitions apply
Nick,
to.
What do you think?
Yeah, Nick.
Well, sure, yeah. We can start with a simple case. They just are undirected. It's just they only matter when you actually do computations on those, right? Like matching those hyper edges. If you're given some left-hand side of a rule. If you just have a data structure, it doesn't really matter, right? It's still going to be represented as a list. You don't care whether it's an order to set or multi-set, or how many cycles or mixes there inside.
Sure. Yeah. But that's what I meant. That because for example, we did some tests already, and in the tests we had this. I can't remember what was called the sort of unordered or something. Was it unordered? There was this function that basically took the lists as unordered lists. Do you remember when we checked that, Nick?
I'm not quite. Well,
I'm not sure. I'm not sure I was there. So.
No, I don't think James was there. No.
Yeah.
So we have
you,
this.
You can look at it. If you have order, that's the most constrained.
Yep.
Right.
Yep.
Case. You just have a list and you just fix the position of each of the hypervectors.
Yeah.
Right.
Right. If you have unordered, it means you should consider all the permutations of those, and everything in between. Right.
Yeah.
That's all basically all the cases.
Yeah, exactly. I mean, this combinatorial species technology sounds fancy, but all it does is it considers all the permutation groupoids that happen between all the collections of elements, right? So, in some sense, once you have something like a list, and therefore all the arrays that come with a higher order sort of lists, you can encode that information just by symmetry properties. Like the question for me was, it might make sense, but I don't know, because I don't know the depths of the language and everything, but it might make sense to want to have something more primitive that is not a list eventually, or but if you say that it's going to be a list anyway, then yeah, I don't see any problems, and that's why everything is a tuple hypergraph and symmetries therein, right? Like
But I had this idea with the incidence matrix version for the hypergraph. Is that it's just a little bit, it differs from the incident matrix for the graphs when you have negative values in the matrix, meaning that you have a different direction of an edge, right? But for the hypergraph, you can encode it, what actually happens for this hyperedge and the vertex by position, because you can look at the hyperedge, a single hyperedge, and look at all the positions of any vertex in this hyperedge, and you can just do some binary encoding of these positions and just do a simple bit encoding of this position of a vertex inside this hyperedge and just record it as an integer inside this matrix. And
do you have that ready?
Yeah, I have this code.
Can we see it? As a quick diversion over on the topic?
I can just post a link because I made it into a Packnet. and it just has 2 examples.
Well, Carlos is unshared, so you may as well just briefly so we get some idea of what you have.
Can check. Can share it.
By the way, can you guys hear the?
I will still post a link. You can
Okay.
paste it in some YouTube or Twitch.
But are you gonna share it? Okay, yeah.
Okay, I'm still gonna share. Have this. I made like 4 functions during yesterday. One is called hypergraph incidence matrix. Then incidence hypergraph is the reverse of that, and I also did the similar thing for the hypermetrics. But okay, I'm just gonna explain what incidence matrix does.
Mm-hmm.
Okay.
If you take a random hypergraph, like this one, with some signature, random 3 RT hyperedges, random 2 RT, random 0 RT, even arbitrary number of those, and you can convert it to incidence matrix, and that would look like something like this. And it's somewhat like a direct analogy of incidence matrix for graphs, but instead of negative integer, meaning the opposite direction of an edge, it's got this like a bit encoding. For example, let's try to decode the second hyperedge, because it should be how many hyperedges in there? 11 hyperedges, and there's like 10 vertices, right? So it's a 11 by 10 matrix. Each row indicates a hyperedge, and each column indicates a hypervertex. Right? So this should encode this hyperedge. So it contains a vertex number 2 as the first position. So you have this. So you basically encode the position of 2 as a 1. So you also have
4, which is given value 2 in
hold on, the columns as the hyperedge.
Yeah. Look, it's row 1, row 2, row 2, row 4, row 5 in column 2.
Yeah. And you just do this bit encoding, because you have vertex number 2, 4, and 5, right? And you
but why is 4 given value 2?
Because it's basically you encode it like that. You have vertex number 2 at the first position, and because you have 3 positions, it should indicate like this bit vector. And this would, like, if you read it in reverse, it's just number 1 in binary, right? If you have 4 on the second position, that would be like this binary vector, and it's number 2 in binary, and this would be number 4 in binary. And you can do it like just for every place of the hypervertex in any place of the hyperedge. You just add them up, you do this bit encoding, and you have this matrix of integers. Basically, that's it.
Really cool.
That's the idea.
So
it's just a representation of hypergraph.
Nick, don't you have to know the order of the hyperedge to the code?
What order?
The order of the size.
What order? You mean the size? The size of number of hyperedges or what?
No. The number of vertices in a hyperedge. If you give me an incidence matrix, I need to know that, right? To be able to reverse.
Well, you can infer it by the integers, right? You always count from the most significant digit, so to speak, right? You can just shoot over it. So you can.
Didn't you say that you have the reverse function, Nick? Can we feed an incidence matrix and get? Okay, so let's see that.
This is the incidence matrix, and this is the reverse, and you can recover the same hypergraph, right?
Mm-hmm. So if I understand correctly, the way you know the number of vertices is by the non-zero entries, right?
In the column.
In the column.
Yeah. So it's a sparse matrix.
Yeah.
obviously. Very, very sparse.
Yeah.
You have more concerns, Carlos?
No. I mean, this is. I mean, when it comes to the actual final language level encoding, I don't think there's. I don't have any strong feelings, because the final structure, like I mean, this whole array algebra is kind of orthogonal to this, because those are operations on the hypergraph themselves. This is a matrix encoding of a hypergraph, right? I mean, it's not.
Yes.
I mean, they're kind of parallel. They're not.
Now, by the way, Nick, has it occurred to you that we could use these incidence matrices in order to assign complexity measures when we're expressing these rules in terms of hypergraph? Is that the idea, or is that one application of it?
But I'm not sure how usually incidence matrix is used computationally for graphs. It's like, I don't know, like you can do some nice linear algebra directly on those. Because I believe that only adjacency matrices are nicely represent the actual graph, so you can do the linear algebra. Incidence matrix nicely encoded in memory. Maybe you can easily convert it to adjacency matrices. So in this case, it's going to be, maybe I should write like incidence matrix, incidence hypergraph matrix to hypermatrix and back. This can also be a thing.
Mm-hmm.
Yeah, exactly. I mean, what I wanted to say is that even though we are saying matrix both in the context of adjacency and incidence, this is kind of a, it's kind of an illusion, that it's kind of a mirage that we're looking at, because even if they look like matrices, they are completely different things, right? They can code very different information, and so one might be led to think, oh yeah, because it's a matrix, I'm gonna, run some linear algebra over it. I think that's going to be very messy. Like,
you've made that point before. Yeah.
So adjacency, the adjacency hypermatrices or arrays or whatever, that I see as basically just the hypergraphs themselves, because it's the literal hypergraph data, right? It's just maybe with an extra ordering. Maybe that's the only thing that is extra in that setting, that you're choosing kind of a gauge choice of an ordering. Like you're fixing an ordering for everything. To turn hypergraphs into...
You can even see that. I have this hypermatrix, which is actually just a list of those graded things, right?
Exactly.
You can just see for the sparse array index where it sets to 1 is exactly the hyper edge, right? This is the hyper.
Exactly. Yeah. Exactly. That's what I mean.
So that's the direct representation.
Exactly. It's not so much that... I mean, I think they are relevant because they call back to all the things that have existed, the tensor networks, all the algebra categories in particular are examples of this. That's why when you asked before about does this general functionality, this general theory, it's because categories in particular fit in that context, right? So they are particular cases of that sort of hypergraph representation. So hypermatrix is just another way of saying hypergraph that is perhaps fixing orders. But yeah, computationally, I have no strong feelings about how you should actually, under the hood, encode things, because I don't have experience actually implementing these things. So sounds good to me, the incidence matrix.
Well, we've almost run out of time, and there's a lot more to discuss.
Yeah.
The fact that Nick has built this nice Packlet, and Carlos, you have this nice structured report. This is exactly the kind of thing that I'm hoping to see from people. Now, the main thing to do is, this report, we need to review it further. There's more to be written. I would like to see even a technical document enjoy I can't say mix now because mix means something else. I'd like to see technical document enjoy dual features, both the formalism and some computational examples, when relevant. If it's the case that we're effectively just introducing it so that it's well understood, so that the objects that we're using are well understood, basically just for formal purposes, I understand that. When it's the case that the formalism is actually informed by or informs the computations that we do, it would be good to kind of show examples of that, so it makes it easier for people to follow.
Yeah, one comment I want to make there, because it'd be good for me to have an idea if we are going to, especially to put my my mind into the right direction. Is there any reason why we would, computationally, why we would prefer doing something like simple undirected hypergraphs first? Because as I understand it, if we are going to use incidence matrix or these other ways of, or the literal encoding of hypergraphs that we've been using, it seems to me that undirected means that we're going to have to run some permutation symmetry on top of things, right? So is there any possibility that that it might be that we want to implement something at the base level to be undirected? Like, I guess I'm speaking of, is it? And because
Well,
you have to do it afterwards, right? Like a sort of symmetrization.
If you're gonna just simply think of patterns, how they exist, for example, the Wolfram language,
Yeah.
The direct natural way is to represent directed way, right? Because it's just gonna be a list, and when you want undirected, you specify some additional pattern objects like odorless pattern sequence. You can say, okay, you can now match any order. That's just a modifier for your pattern.
Yeah. No, but this is exactly what we did in that meeting we had. That I think is orderless or something like that. That you in the pattern matching you only require you require the flexibility. But my point is about efficiency in some sense, right? Like if we had a way to have a data structure that is undirected itself, right? I guess it will take much less computational effort to do the pattern matching, because it is primitively an undirected bag of vertices. Maybe this is just not possible.
I was kind of thinking how would like any replacement or rewriting would look like if you given this hypermatrix or incidence matrix. If you like have a hyperedge and you know that you match some specific pattern against a vertex, you can first find an actual vertex among your vertices. Then you find the second vertex and the third one. If your hyperedge is IRT3, okay, you found all the vertices. Now you scan from all the hypergraphs where it's not zero, right? You can kind of, your sparsity can work for you in this way. Because an incidence matrix is sparse, first you find all the vertices in any order you want, right? But in order to unordered, and then you find a hyperedge that matches it somehow, right?
Mm-hmm. Yeah, I mean, yeah. I guess I was just wondering about efficiency, because in reality, the models of systems that we might end up wanting to describe or to simulate in some sense, not emulate in this case, are things like chemical reactions, right? Or some kind of chemical computing and things like that, where you just have presence of reactants as a condition, and there's no order because there's some kind of solution, right? Some dissolved substances or whatever. So it's just the presence of types of kinds in some sense, and that makes the hyperedge, and the replacement happens at the level of it is just a sort of a mix of these things, like a this solution of these reactants, and reality computes in that way in some sense, right? Like, I mean, in these systems at that level of coarse graining, there is such thing as bag rewriting, right? Like there's a bag of reactants and you get a new bag of outcomes of the reaction, and there's just a bag rewriting, right? There was no sense in which these reactants were actually a list, but there was some symmetry and it was equivalent, blah blah blah. So I was not making any technical comment, but more of a, is it possible or is it reasonable to think that this will be a factor in Mathematica? Maybe not, because as you say, if you just encode it, it might be just faster. It's not a problem. It's just a comment. Okay, so we go with that implementation, right? We go with incidence matrix, and to make it.
But we can support multiple representations. I'm not advocating for which one particular one. It's like even graphs. I already said that graphs in the Wolfram language implemented with multiple representations. You can convert back and forth. Under the hood, you can convert between them.
But the graph has this primitive data structure, right? In Wolfram language.
No, you have the data structure, which is exposed to the user, but under the hood, it can use multiple representations.
Yeah.
It can be represented by a sparse matrix or by incidence list of edges.
Yep.
Simply.
Yeah.
Or some simple representation. Something like that.
Any hope of getting like a basic data structure in Wolfram language that is hypergraph?
Well, I was hoping this new packet is going to contain one of those. So
Nice.
right now it's just 4 functions, but we can just add functionality to that.
Nice. Cool.
Which is at this point missing from the repository. It already contains a bunch of hypergraph functionality, but this one is just gonna, I hope, gonna extend it further.
We should probably, I mean, this conversation doesn't feel finished. We have Carlos's report, we have Nick's Packlet. I should put a meeting on the calendar tomorrow. I think we should just continue this. Does that sound okay? Guys, Carlos?
Yeah. So.
Sure.
Yeah.
Okay. Because we didn't even get through Carlos's report, and the thing about the report is it's a good summary, but I'm sure that there are. I could take a look. I imagine that there's a discussion of kind of next steps. We haven't even gotten to the category side or the complexity measures.
Yeah.
So this document, in some sense, is to help us plan, but because we haven't even gotten through the whole document, we're not even at the frontier of what our plans are, and at least in terms of this meeting. So I'd recommend let's have a meeting tomorrow.
Well, we're going to discuss scheduling now, so let's talk about it in our internal meeting.
Yeah. I guess live stream viewers don't have to see a schedule meeting.
Yeah.
All right, guys. All right. Okay. I'll see you at the next thing. Thanks, viewers. Thanks, everyone.